Okay, so today we will discuss the two main coupling terms we have. The one is that due to the forces, the mechanical structure will deform, and we will have moving, deforming bodies within the magnetic field, and that is something which is a very complicated task to be included in any finite element software, as we will soon see here. So actually we have derived the partial differential equation in this sense that we have here our classical curl-curl operator, where we have the reluctivity as a function of the magnetic flux density, and we have some given current density in a coil, for example. We can come up in any conductive bodies getting eddy currents due to the time change of the magnetic vector potential. And here the very important so-called motional electromotive force term, where in conductive bodies we get the additional current density, which is computed out by the cross product between the velocity v and the magnetic flux density, expressed here by the curl of the magnetic vector potential. What we should not forget actually is that clearly the magnetic vector potential will also change in any case, even if we have moving parts where the conductivity is zero, so we would not have this additional term, but the configuration somehow changes. And that is the big challenge, which is shown here. Very simple. So we have a lift magnet, and we assume that the ferromagnetic bodies we have here, so this part here, where this part here, and also the part which is levitated, let's assume they have no electric conductivity. So we will not have this additional term here. Anyway, we know that when the air gap is decreasing and decreasing, we will have a change in the magnetic field within the core parts, the ferromagnetic core parts, but also concerning the stray field. And what I have written down here is, when you model this simply by magnetic resistances, you can compute the relation between the current in the coil with the number of turns and the magnetic flux phi m. And what we have here are just the magnetic resistances you have in air, you have within the ferromagnetic part, which is this part here, and the second one, which is levitated, which would be this part here in this sense. And what I currently see, there is a small mistake, so you should multiply this by 2, clearly, because we have two air gaps. There is an air gap and there is an air gap. So the magnetic flux clearly depends on the position, and this is also something we have to take into account, which is not explicitly shown up here. So the question is, what do we have to do in order to take also such effects into account? And that brings us to the following situation, that we have to consider that any material point you have within a body is a function of space, so of x, and of time. And what we are now interested in is the change of the magnetic vector potential within a time step delta t. And the total change, if we write it down first with finite differences and then letting go delta t to 0 to come up to, at the end, the partial differentials, we have the following, that we have to evaluate the magnetic vector potential at the new position. So this material point here, P, at time t and position x, it will change the position x to this new position here, which is the position x plus delta x at time t plus delta t. So we have to take the difference when we evaluate the magnetic vector potential at position x plus delta x and time t plus delta t minus the value we had at the previous position, which is the position x and previous time t divided by delta t. So if we do a Taylor expansion, yeah, so this is our classical term where you can do a Taylor expansion. We assume delta x as well as delta t is small. Then what we get is this expression. So we clearly have our developing point, which is the position or the vector potential at the old position x and old time t. And then we have the changes of this vector potential with respect to time and space. So with respect to time, it's the partial derivative and delta t. And with respect to space, we have x, y, and z coordinates. So we have the partial derivative of the magnetic vector potential with respect to x, but the position itself changes. So we have to multiply it with the partial derivative of the position x with respect to t and delta t. And the same we have for the y coordinate, so the change of the magnetic vector potential with respect to the y coordinate and with respect to the z coordinate. And that we can rewrite because the time derivatives of the change in the position is nothing else as the velocity. So we can rewrite it as shown here by our evaluation point at x and t, the change with respect to time delta t, and the change with respect to space multiplied by delta t. Now we can here divide this by delta t, substitute clearly here also within our equation, and we let go delta t to 0. And what we get then is the total time derivative, as shown here, of the magnetic vector potential, which also includes that each material point is changing in time. And that is why we have the classical partial derivative of the vector potential with respect to time, and this additional so-called convective term we have here, which is the velocity dot product with the nabla operator and operating on the magnetic vector potential. And what is too much here is this delta t, so we have to cancel it out. That's a mistake on my slide. Okay, so we see that this is actually what we should get out, because we have a change in time and each material point will also change within time. We have now a very interesting vector identity which we can explore, and that is that we can rewrite our classical motional EMF term as follows, as one term where we take the gradient of the dot product between velocity and magnetic vector potential, but the nabla operator is just operating on the vector potential. So V has to be treated as being constant. That is why we write it nabla with the index A minus gamma, and then we have this classical convective term we also have seen before in our substantial derivative of the magnetic vector potential. Now what we have to notice is that in this substantial derivative, we dA dt, we have not included this term here, which means when we really introduces this substantial derivative, which means we always compute the magnetic field on the actual deformed geometry, then this term is not included, which means, since this is also physics we have derived, we have to do it within our formulation. So our formulation now changes to this partial differential equation, where we have now as a new term not only the partial derivative, we get the substantial derivative of the magnetic vector potential, which includes the partial derivative with respect to time and this convective term, but we have to correct it by this term here. This is a very interesting term. As you can see here, it is a gradient of the dot product between the velocity of the solid body and the magnetic vector potential, but this operator is just operating on the magnetic vector potential. We never have any problems in 2D, in the plane or axisymmetric case, because you know the magnetic vector potential is going, let's say you compute in the xy plane, then the magnetic vector potential has just a z component, so it is pointing into the plane. And the velocity v clearly will be the velocity you have within the plane where any elastic bodies deform or any solid bodies move. So the dot product will be always zero. And that's the same case for the axisymmetric setup, because there we have a magnetic vector potential just going in circumferential direction, and the velocity just can have a r and z component. So as a result, we can say that in order to include all the effects, we always have to compute the magnetic vector potential on the actual deformed geometry, and which automatically has then this term here. So I just want to show it. So which automatically always has this term here, but we have to correct it in order to really physical model the motional EMF term, which is not necessary in 2D, this term, because this is always zero, but in 3D you have to take this into account. Now this is a big challenge, which I want to show here with this very simple setup of the lift magnet. It is just, as you can see here, we do a computation in a cross section, and therefore we have the upper part of the coil, the lower part of the coil. Here, for example, the current is going in, here the current is coming out. We have the iron core, and we have here the moving part, and due to the electromagnetic forces, when a current is flowing through the coil, a magnetic field will come up, and we will have here so-called pole force, which we will discuss shortly, along the poles here, and which will then lift this ferromagnetic part towards this iron core. So clearly what you can see, what does this mean to compute always the magnetic field on the deformed geometry? That means when this part is moving, then I have to add to all the coordinates the mechanical displacement. But you see, when I add the mechanical displacement on this node, then these elements here, the first layer of elements along these moving parts, they get thinner and thinner, and after some time perhaps you even have an overlap, and that is not possible to be computed. So the idea is to also try to change the mesh here. I just take out this part of the mesh in such a sense that we not only add the mechanical deformation of the nodes on the surface here to the original coordinates, but distribute the mechanical deformation in the whole air region, which is shown here in gray. That means when you do a mechanical, in the magnetomechanical computation, you first compute the electromagnetic forces, then you do a mechanical computation with known electromagnetic forces, you get a new displacement, and this new displacement you put in a further computation, in a so-called pseudomechanical computation. You put it as a boundary condition along this part here. So you have a third computation, a pseudomechanical computation. On this region here, you set, for example, along these boundaries, the mechanical displacement to 0, because we assume that this part is fixed. Along the moving part, we apply the mechanical displacement we have obtained by the mechanical computation, and then do this so-called pseudomechanics. And that will lead to the following, that not only the first layer will be deformed, but all finite elements within this region will also get a deformation. And so you redistribute the mechanical displacement on the surface also within the inner part of this gray computational domain where you compute the pseudomechanical displacement. So this is an extra computation just to redistribute this mechanical displacement. We also call it a smoothing mesh technique. And it even has the benefit you can use any mechanical material properties, even anisotropic properties, so that the deformation of all these elements will be small in such a sense that you do not get very badly shaped elements. And that I will show you on the next slide. And here you can see what actually happens. This is for some different time steps. As you can see here, for the first time step, you see that these finite elements now get thinner, but not only this, also these elements here. So along, and you see also deformations in these regions here. Yeah? But still, if you look at the mesh, and that will be the mesh on which you compute also the next magnetic step, is still a good mesh. Now, if you get further moving of this part, you see still that this deformed mesh, which you use for the electromagnetic computation, has good properties. And clearly, if this movement goes further up, you will get some problems within this region here. Perhaps the blue one is not as good, so I should use a different color to see it better. Let's take the green one. So especially in this region, so especially in these regions here, you get the strongest deformation. So you see it also here on this side, it is symmetric. So you see this is actually now these deformed elements. Still they have a shape where I would say that is not a problem. What you cannot handle with such a smoothing mesh technique is a contact problem. Yeah, because if really this moving part gets into contact with this iron core, well, what to do with the finite elements in between? Yeah, so there, from time to time, you then have to do a remeshing of this part, or there are also some other methods available, which are called fixtures domain methods, but not for all cases they are working. So if you have such setups where no mechanical contact occurs, then mainly you can do this with this smoothing mesh technique, which means that in the air region, where you also have to compute the electromagnetic field, you solve an additional problem to get a smoothed mesh and not any penetration between finite elements. Okay, so actually we have this part here because you have electromagnetic forces, and the two main forces are the Lorentz force and the Paul force. I think the Lorentz force is well known, the computation. If you have, as shown here, any current carrying conductor, so we have here the current density flowing in this direction, and this is within a magnetic field B. Then according to the cross product, you come up here with the total force when you also compute over the volume, or you have the force per cubic meter, so force density, which is the cross product between J and B. Okay, so this is when you have here any conductive bodies, and these bodies have more or less the same permeability as the ambient air, which is, for example, the case for copper or aluminium. However, if we have different magnetic permeabilities involved, as it is, I would say, the standard case, then also pole forces in addition come up, because you have a change in the magnetic permeability from one region, as we can see here. Let's say this is region 1 and this is region 2. And then exactly at the interface, you have to evaluate this volume integral, which is a very nasty volume integral. You can also derive why this term looks like this. It is the magnetic field intensity squared over 2, and you have to take the gradient of the magnetic permeability. How to take a gradient of a magnetic permeability at the interface where the permeability is jumping? So that is something which is not sensible to be evaluated, and that's why we can transform it to a surface integral, which we will discuss soon, which is now as follows. You just integrate over the surface. So this is our surface, the interface. No, not this one. So this is our interface where the magnetic permeability changes. Typical interface would be iron-air interface. And as you can see here, what we need along this interface, we need the normal component of the magnetic induction and the tangential component. And you see why we do this is clear. We know the tangential component of H is continuous and the normal component of B is continuous. And then you just need the differences of the two permeabilities as well as their inverse, so 1 over mu 2 minus 1 over mu1 scaled by the normal component of the magnetic induction squared. Okay, and this we will now look up how we come up to this formula, and that is as follows. So we assume now that we have exactly such an interface, and we cut out of this interface, as shown here, such a cylinder, and which is going from radius r1 to r2 with a height of h, and clearly at the end we want to have here to go h to 0 in order to come up to our interface, which is clearly this part here. Yeah? So we have a small cylinder with a surface here given by delta gamma and a volume given by delta omega. Now we assume no surface currents here, and the total electromagnetic force delta F in this sense would be just for this small body that we integrate our force density we have seen before. So h squared multiplied by the gradient of the permeability over this small volume. And that is the same since we assume that it is so small. So on the surfaces, we have the same properties. We can put out the delta gamma, and so we just have to integrate in radial direction from R1 to R2 our volume force, which, as shown here, is our magnetic field intensity squared multiplied by the gradient of mu, and we have to integrate it in radial direction. Now the question, how can we do this? And the first one is that we have the following relation between the total change of the permeability and the gradient of the permeability. And that is given that this total change is the same as taking the dot product between dr and the gradient of the permeability, as we know. And since we assume that dr is going in normal direction, the normal vector of our surface or interface, we have just this dr gradient mu, and so we can divide this equation by dr. And doing this, we see the following, that now the gradient of mu dot product with the normal vector, as shown here, is equal to the total change of the permeability with respect to the radial direction. And that we will use now in our formulation. As you know, we now project our delta F in normal direction, so taking the scalar product with n, which means we also have here the scalar product between n and the gradient of mu. And that we can substitute, clearly, that we can substitute now by the total change. So this term here is substituted by this term, which means what we get is the total change of the permeability with respect to the radial coordinate and integrating over the radial coordinate, which means that instead of integrating from R1 to R2, we have to integrate the permeability, as shown here, from mu1 to mu2 of a value h squared. Now, what we have to take into account that h itself is continuous, but just a tangential component. The normal component can jump, and that's why we rewrite the magnetic field intensity as a vector within its tangential component, multiplied the tangential component with the tangential vector, unit tangential vector, and the normal component multiplied by the normal vector. So we have here a vector just pointing in tangential direction of h and in normal direction. And just the same we do for p, so that because we know that the normal component of p is continuous and the tangential component of h is continuous. So we also get here out a vector just pointing in tangential direction of the magnetic flux density and in normal direction. Okay, and now we also know that we have the constitutive equation between h and p, which we will clearly explore. And so this term h squared, which is the dot product h dot h, as shown here, we now substitute it in such a sense that we substitute the normal vector of h by b via the constitutive equation. So it is the vector b just in normal direction over the permeability plus the tangential vector of the magnetic field intensity, and the same clearly on this side. And when we take the dot product, we clearly know that the dot product between a vector in normal direction and the vector in tangential direction always gives 0, which means we get out the following, that we have here the normal component squared over the permeability squared plus the tangential part of the magnetic field intensity squared. And that we now can explore in our formulation. So we already go here for delta gamma letting go to 0. So it is the derivative of the force with respect to the gamma, and we come up to the force density in Newton per square meter when we let go this delta gamma to 0. And in our case, it is then the following. We already have derived it before, that we have now to integrate over the permeability, and we have for the first term, as you also have it there, we have this h squared or h dot h expressed by this term. So we have to integrate once the term 1 over permeability squared, and this is scaled by the normal component of the magnetic induction. And once we just have to integrate the function 1 from the limits mu1 to mu2 and scaled by ht, so the tangential component of the magnetic field intensity squared. Okay, that is an easy task for us, and that gives us the following, that we have here once a term which is proportional to the normal component of the magnetic induction squared, where we have 1 over mu2 minus 1 over mu1, and once we have the tangential component of the magnetic field intensity squared, and it is scaled by the difference of the two permeabilities. Yeah, and we also have here a rule of thumb, and that is the force is always pointing in such a direction that it tries to make the space where you have a lower magnetic permeability smaller, which means it's points from region with larger magnetic permeability to region with smaller magnetic permeability. And that's also why in our case for the lifting magnet, the moving part is moving towards the iron core. So we also can rewrite it clearly, this so-called force density or surface force density, it is Newton per square meter, as the value itself, and it is always pointing in normal direction. So this is something you can directly evaluate on the surface. Concerning the finite element method, one has to be a little bit careful. You should have good shaped elements in the air region attached to your ferromagnetic region, that this computation is accurate. A second approach, how you can compute the electromagnetic force, and here I mean the total electromagnetic force, so both the pole force as well as the Lorentz force, is by our standard principle, the principle of virtual displacement. This is a principle coming from mechanics, and it just tells if we have a virtual displacement, then the change in energy is given by the force acting on the body in the direction of the virtual displacement, which means in our case we have to compute the magnetic energy, and then, as you can see here, the magnetic energy, in this sense we assume it that we have a linear relation between H and B, which we actually will have, because that is the energy we compute in the air region, and have to do this virtual derivative of this energy with respect to the r coordinate, and then we get the r component, so that's the direction, and then we get the r component of the magnetic force. So classical, we will have to do 3 evaluations, one in x, one in y, and one in z, when we have Cartesian coordinates. So this is the standard setup. We assume that we have here this moving body, and what you actually do is that you take the first layer of finite elements surrounding your moving deforming body where electromagnetic forces wants to be computed. You fix all the nodes, the outer nodes, and just the nodes on the surface of this body can have a virtual displacement. So the virtual displacement delta R is set to 0 in this node. Fixed node means that this delta R is 0. Okay, so how does this work? So we now go and look for the total force. In a finite element approach, we have to evaluate this for all our finite elements E surrounding this body. We have to compute that would be the correct expression for the magnetic energy. We have to integrate H dot product dP from 0 to P, and then integrate over the volume, over each element volume of each finite element volume in order to get the magnetic energy corresponding to this element, and then take this variation with respect to the R direction to get R out. Now, if we do this, then we can have a variation due to the fact that we have, or first of all, I should say, we first substitute this relation here by this simple one where there is still some mistake. Okay, I have not seen. That should be away, and we integrate clearly here over the volume. So we have assumed here, since we integrate over elements within the air region, we have the simple relation between B and H over the permeability of air, which is mu0. So B, I should write here in this case, is simply mu0 H, which we use here as a simple constitutive relation. Okay, and when we do the variation, we can have the variation according to a change of the magnetic field B and due to a change of the volume, because when we do a displacement, the volume of this finite element surrounding the body will change in their shape. Okay, this is actually nothing else as B squared. So when we do such a variation, it is nothing else as 2 times B dot product with the variation of B. These two and these two, this 1/2 cancels out. Therefore, within this term, you don't see the 1/2. And in this part, we have the variation of the volume itself. Okay, now if we go to this finite element setting, then the force on each finite element node I, as shown here, is nothing else that we sum up all the finite elements which also have this node I included, which means if we have a node somewhere at the corner, then we have more than one element clearly belonging to it. If not, it's mostly just the two neighboring elements. So we have to integrate then for this so-called nodal force acting on it our term as we had before. The difference is just that the sum goes from over all elements where this node I belongs to. And we have to evaluate this part here within a finite element context. Okay, so the details you can find in my book, because this second term to get it in a setting what we want to have. Okay, so now coming to the final coupled system of ordinary differential equation as written here is as follows. We assume that we do a partitioned ansatz, which means we solve the mechanical PDE separately from the electromagnetic PDE in such a sense that we first compute the magnetic partial differential equation in a semi-discrete Galerkin formulation. Here still continuous in time. We get this system of ordinary differential equation where we have the magnetic mass matrix. As you know here, the electric conductivity enters in. That will depend on the mechanical displacement. That's why we always have to compute it on the updated geometry. We have the magnetic stiffness matrix, which depends clearly also on the mechanical displacement, but due to material nonlinearities, that the permeability is a function of the magnetic induction, it also depends on the magnetic vector potential. Yeah, and then the right hand side, which includes any excitation by currents, for example, also can depend on the velocity, mechanical velocity, as well as on the displacement, and it even can depend when we have any permanent magnets, for example, it even can depend also on this magnetic vector potential. So we have quite a lot of nonlinearities, but when we assume that our deformed geometry is frozen for the part when we compute the magnetic field, then all the dependency on the mechanical parameters are gone, and we just have the nonlinearity according to the nonlinear constitutive material law between the magnetic flux or magnetic induction and the magnetic field intensity via reluctivity or permeability. On the other hand, when we have computed our magnetic partial differential equation, within a time step, we now know the magnetic forces, and then this term here, we assume that we have no further additional mechanical forces acting on our mechanical structures. Then this term is known. Let's say it is according to the fact that we freeze now the magnetic field, and we can put this on the right hand side, and then clearly we can also include any nonlinearities due to large stresses or strains when you have to take this into account, and the mechanical stiffness matrix will depend on the displacement itself, but the mass matrix will be a linear matrix, and also the damping matrix when you include any damping. Okay, so that also means now that we get, when we solve now for a time step this mechanical algebraic system of equation, we get a new deformed structure. And with the new deformation, we just try to redistribute this deformation within the air regions, and then again compute on these deformed meshes our magnetic field, get then a new magnetic field, compute the forces, go back to the mechanical equation, and so on. Which means very similar as you solve a nonlinear single partial differential equation, we will also need here a stopping criterion in order to know when we can go on to the next time step. And the stopping criterion is very often what is used is the mechanical displacement. So you see we compute the mechanical displacement at time step n+1, but we have this iteration counter k. Yeah? And so the difference in the iteration k+1 and the solution at iteration k, you compute and normalize it to the value you have just obtained when you solve the mechanical equation for iteration k+1. And again, as we had for the stopping criterion, we also use here, since it is a relative norm, something like 10 to the power of minus 3, which is somehow 0.1%. You still have changes, but this is so small that we can say, okay, this is now a converged solution between the mechanical and the magnetic field, and we can go on to the next time step. And this procedure is illustrated here just as a computational scheme. So what we can see here is what I just have told you, that we have here nothing else as our magnetic part, which also needs to be solved iteratively when we have to take into account the material nonlinearity within the computation of the magnetic field. And then when we have the magnetic field, we can compute, very importantly, these magnetic forces. And then the magnetic forces are known, and we go on and can compute the mechanical field with known magnetic forces. And then we clearly have to check. This could be also a nonlinear computation, because you take material as well as large deformations into account within your computation of the mechanical field. And that means we then have, after this is converged, we have a new mechanical displacement in all our finite element nodes within the solid elastic bodies, and we check there how much the mechanical displacement has changed. If it is too much concerning our criteria, we have to go back. We have to compute the magnetic field. Please consider on the updated geometry. Yeah, so we have to add the mechanical displacement to the coordinates of all the finite element nodes where we compute the magnetic field. If these displacements are too large, you have to do some smoothing, as we have discussed. So you compute this kind of pseudomechanics to get a new deformed mesh which is consistent and where you can compute the magnetic field. If this is not possible, you have to remesh for the computation of the magnetic field. Yeah, and if you have a new magnetic field, you get new magnetic forces, and you go to the mechanical field, get a new mechanical field, new mechanical displacement, and check just the convergence criteria we have discussed. Further convergence criteria for this outer iteration loop between the magnetic and the mechanical field could be clearly also, in this sense, the mechanical, these electromagnetic forces. Because if the electromagnetic forces are not changing, or the change is so small that you reach the convergence criteria, you should also measure this in a relative norm, as I have shown before for the mechanical displacement. So this would be also a good stopping criterion for this outer iteration loop between the magnetic field and the mechanical field. So this is the standard approach for magnetomechanical systems, that you separately solve the two fields, but you do an iteration between the two fields so that you get a strong coupling. And when you get a convergence between these two coupled field, then you go on to the next time step and not before. This is very critical when you have not such iterations. That perhaps will work when you have a very, very small time step, but for most reasonable physical time step, you converge then to a totally wrong solution. So you need this outer iteration loop within each time step to converge and get a converged solution between the two physical fields, the magnetic and the mechanical field. Okay, and that also shows us that even if your computational mesh is not so large, that it could take quite some time when you have to compute for a lot of time steps. Okay, so I have overseen the chat, but now I'm looking at the chat. Regarding the mechanical forces, no, we not only have the Lorentz force. So as we have seen before, when we have any change, and that is in most, not in all, but in quite most actuators, as well as electrical machines, you have clearly an iron core in order to guide the magnetic field, and then you have at the interface between the iron core and the air, you have these pole forces, these surface forces. And within the volume, when there are also additional currents, that could be the currents in coils or that could be eddy currents, you have these additional Lorentz forces. If you compute the forces by help of, I just go back, by help of this approach, which is the virtual displacement approach, then this formulation includes both forces. Yeah? So you don't have, in addition, also to compute here the Lorentz forces. So this formulation includes Lorentz and pole force. However, if we go back and look at these two different formulas, as I had shown you at the beginning, yes, here it is, then you can individual compute by the first formula as shown here the Lorentz force, and in addition you can compute the pole force. So you can differ between these two forces, but if you have such a setup where you have within a body any eddy currents, or you compute the Lorentz forces on coils where currents are flowing, you have to compute the Lorentz force, and in addition, in most cases, you will have devices where you have such interface where the permeability is changing, an iron-air interface. You also have to compute these pole forces. Yeah? So both are active. You can have additional forces when you have any liquids, for example, which can be also magnetized and so on. But this is then for very special active materials. For the standard case, if we look at the transformers on electrical drive and so on, you just have these two kind of forces. And you get it in once when you use the virtual displacement method. When you want to compute it separately, which also makes sense to see how large is the pole force, how large are the Lorentz forces, then you have to evaluate these two formulas, and this will enter then the right hand side of the mechanical equation. Okay, I hope I have answered this question you put into the chat. Okay, so this is more or less now the end of our first part in the course, which considers the coupling between the mechanical and the magnetic field. And you see it can be as complex as possible, especially when you consider the motivation example of the magnetic valve, where this has even a contact problem to be taken into account. Then we will not be able to solve this with this smoothing mesh technique. You can use this for some time, and then it will be necessary to remesh your computational domain, which also means you have to interpolate your results from the old mesh to the new mesh, which is also very challenging. Okay,